So chapter 4 is about discrete random variables. Discrete, as you know, is basically a variable that takes values like 0, 1, 2, 3, and so on. It could be like number of students absent in a class. So if you collect data on that, your numbers will look like 0, nobody is absent, or 1, or 2, and so on. It could be number of customers that walk into, let's say, Target between 8 and 9 a.m. So again, the numbers will look like 0, 1, 2, 3, 4. Or it could be number of laptops somebody purchases from a local store on a given day. So it could be again 0, 1, 2, 3, and so on. Number of tickets people get on a freeway. So that could be like 0, 1, 2, 3. So all those variables are discrete because they can only take some specific values. Most popular distributions that we discuss here, 3 of them. One is hypergeometric, binomial, and Poisson. So for a given situation, you may need a very specific kind of distribution because even with discrete data, there are so many different situations. There may be a situation where you are doing sampling with replacement, you are doing sampling without replacement, or some other thing. So because of a unique situation, one of the 3 may fit in better compared to others. Let me give one example. So when somebody wants to purchase a Tesla car, like they have a business model where everything happens through app. There's no store. You start with the app and order. So one of the options they give is for color, it could be free. It could be just one color that you can get free. And for other ones, you have to pay $1,000 or sometimes more than $1,000. So somebody may be interested in this kind of question. What is the probability or what is the chance that a customer prefers a free color option? Because a company like Tesla may want to get an estimate like how many they should make with a specific color depending on what customer preferences are. So how many of them choose free option, how many choose like specific colors? Obviously they will be interested in that. What is a random variable? When we talk about discrete random variables, so random variable is basically outcome of an experiment or trial. We can represent by uppercase X. So that's a convention. We use uppercase X to represent a random variable. So that could be number of customers that prefer free color option. Although we are saying free, it's not really free because we are already paying for the car. Free option only means that compared to other colors where you have to pay $1,000 more. So this is like a free. Depending on if you're collecting data every hour or every day, so your numbers for X may vary from 0, 1, 2, 3, 4, 5, and so on. Let's look at another example. I used to wonder, for example, why people write EG. Anybody knows what is this EG? Why do we write EG, for example?
Latin.
It's Latin?
Yes.
What it stands for, E and G?
Exempli gratia, which means for example.
Exempli gratia, so for example. So that's why we write EG. So that is for example, number 2. Your experiment could be toss of, let's say, 3 coins. So that could be a trial or experiment. You're tossing 3 coins together. And in this example, our random variable we can define as number of heads. So how many heads you get when you toss 3 coins? In the definition, there was a word called outcome. So every experiment or trial has an outcome. So I can write outcome for this trial and there are only like a certain number of outcomes possible. If you toss 3 coins, it may happen that all 3 are head, or first one is head, second head, third could be tail, or first head, second tail, third head, or it could be head, tail, 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 head, head. It could be tail, head, tail, 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 head, and then all 3 tails. So these are all possible outcomes of tossing 3 coins. There is no other option available, right? Did I miss anything? Anything that could have happened? Anything else that could have happened? Because it's only 3 coins, it's difficult to miss all the options. So I have listed everything. There are like 1, 2, 3, 4, 5, 6, 7, 8 options or outcomes. For our random variable x, so x is number of heads. So if it is first outcome, the value of x will be 3. Here it is going to be 2 because there are 2 heads. I'm just counting number of heads. So you get 2, 1, 2, 1, 1, and 0. So this random variable, you can see here, it takes like 4 different values, 0, 1, 2, and 3. X taking these values 0, 1, 2, and 3. And that's why we call x as a discrete random variable. We cannot get a number in decimals here. So using this table, we can create a small table like this, where you have the values of x, 0, 1, 2, and 3. And then you can count the frequencies. So how many times 0 can occur? Only once. All 3 are tails. So this is 1. How many times 1 has occurred? 1, 2, and 3. So 1 has occurred 3 times. How many times 2 has occurred? You can see there is 2 here, there is 2 here, there is 2 here. So 3 times. And how many times 3 has occurred? Just once. Now if you divide each frequency by its total and call it f of x, what is the total? So 1 plus 3 is 4, and 4, 8. So this should be 1 by 8, 3 by 8, 3 by 8, and 1 by 8. So this column is probability. So that is called probability, and it will always add up to 1. Total probability is always 1. So this small table that you see, it shows us how the probabilities are distributed across different values of x. So how these probabilities are distributed. So this is what is called probability distribution table. It tells us how probabilities are distributed. Now, to be a valid probability distribution table, there are 2 rules that such a table has to follow. Rule 1 is that each probability has to be positive. It can be 0 or more, but it cannot be negative. F of x is greater than or equal to 0. Rule number 2, total of fx equals 1. Total of all the probabilities should always be equal to 1. If you see any fx value which is less than 0, then it is not a probability distribution table. If you see anywhere, if the total will not add up to 1, it is not a probability distribution table. So both have to be fulfilled. How does this help? Remember, this kind of question that we started with. What is the probability that a customer prefers free color option when buying a Tesla car? So how do you calculate that probability? That's where this, whatever we discussed just now, actually will help. We use a short form actually when we write. So this is a shortcut that we use. It stands for what is the probability that x equals 2. So you have this 3 tosses of a coin, or you're tossing 3 coins, and what is the probability of x equals 2 means what is the probability that 2 of the coins will show heads out of 3. So instead of like writing that long sentence, we simply write P of x equals 2. Because we have already defined what is x. X is number of heads on 3 coin tosses. Probability of getting 2 heads is 3 out of 8. How do we know 3 out of 8? We listed all the possible outcomes, and we identified that we have 2 here, 2 here, 2 here. So 3 out of all possibilities, which is 8. So 3 out of 8. I can write this as, so number of ways you can get 2 heads out of 3 divided by total number of outcomes that is possible. So number of ways you can get 2 out of 3, we listed everything and we find there are 3 such cases out of 8. So let's go to one more example now. This is example number 3. So suppose I define a random variable x to be, suppose that's our random variable, and you have a sample of 50 customers who are yet to choose. So we need like those 2 numbers, number of ways you can get 2 out of 3. So suppose we are interested in, out of 50, what is the chance that that number is 10? So out of 50, 10 customers preferring free option. So suppose we are interested in finding, let's start with the denominator. What is the total number of outcomes possible? So given this situation, when it was like 3 coins, we could write down and then double check that we have not missed any option. So head, 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 tail. So we can visibly see what we have, and then we can just check and see that we have not missed anything. We are fine. So we have the entire list. Now when you have 50 customers, how do we know what is the total number of outcomes possible? So there is a formula for that. So total number of, so that is one thing that we definitely need. So this number is easy to find. It is 2 to the power of 50. Why 2? Because we have divided our experiment in such a way that the outcome is either this or that, free option or a paid option. There are only 2 outcomes possible from this experiment. So this 2 here is basically free or paid. So free option or paid option, because there are 2. If we had 3 options, we will write 3 there. But right now we have only 2, so we are writing 2. And then to the power of 50, because we have 50 customers. So that 50 is number of customers. If you recall the previous example, we had 3 coins. When you toss a coin, you get head or tail. So 2 outcomes. So denominator would be 2 raised to 3. So what is 2 to the power of 3? 2 times 2 is 8. So there we did not do this calculation, we simply counted and we got this 8. But now it is very difficult to write down all possible combinations. So at least this one tells us that if you start writing all possible outcomes, then it is going to be 2 to the power of 50. So that's a big number actually. That many million. So 1.1 billion million. So you will immediately notice that that approach that we used last time is not going to work here. Nobody is going to sit down and write 1 billion million outcomes by hand and then figure out of these, this one is where a customer is choosing free option. So count that and divide by this, and then you can say that, okay, probably this is the probability that 10 customers will go for free option. So it is not possible to do like manually. That's why like statistics is all about working smart. So we have to figure out a way that we can still do it in less time. So we don't have to write like these many times all the outcomes, and then probably if we make a mistake, then we have to go back and redo the whole thing. So that is your denominator. Now how do we figure out number of ways to get 10 out of 50? Just like heads, getting 2 heads, it happened in so many different ways. One time we had head, head, and then tail, and then head, tail, head, head. So how many ways we can get 10 customers choosing free? It could be the first customer, second customer, third, and so on. Or first may go for paid option and so on. So what is the number of ways? So to figure that out, there is a formula in statistics that we use. It's called combination. We are choosing out of 50, 10. In how many ways you can select 10 out of 50? You may have seen this earlier, 50 factorial divided by 10 factorial and 50 minus 10 factorial. Factorial is, for example, 50. You start with 50, keep on subtracting 1 and multiplying, like 50 times, 49 times, 48 times, 47 times, till you reach 1. So it's going to be a big number. Divide that by 10 factorial times 50 minus 10, which is 40 factorial. So this is how we find how many ways you can get 10 out of 50. If you go to Posit Cloud and use R, you can enter something like this, how many ways you can choose. So they use a function name called choose, all lowercase. So out of 50, we want to choose 10. So how many ways are possible? So if you type this and run, like this is using R in Posit Cloud. So once you enter that, that will give you an answer. 10, 272, 278, 170. So once you run that line, this becomes your number. How many ways you can choose. Using combination for figuring out these numbers saves a lot of time. Instead of like manually trying to write all possible outcomes and then counting how many, you can directly do this. Hypergeometric distribution. First discrete distribution is hypergeometric distribution. And when can we use this? So the conditions we should have is trials are when trials are not independent. So from one trial to other trial, you do not have something which is independent. And the other thing is probability changes. probability changes from one trial to other trial. Under those conditions, we can use hypergeometric distribution. So just as an example, suppose you have like 52 cards, a pack of cards. So if you pick up a card, what is the chance of getting an ace out of 52? If you select a card, what is the chance of getting an ace? Yeah.
1 in 13. 1 in 13.
So basically there are 4 aces and total 52 cards. So 4 by 52, that becomes 1 over 13. Yeah. So I will write down just without doing any math. So probability of getting an ace is 4 by 52. Now you take a card. Suppose you get the first one, first card is an ace. Now you want to draw one more card. Now you are not putting this card back. You are drawing one more card. So first time your chance was 4 over 52. What is your chance now of getting an ace? 3 over or 51, because you already took a card. So second time your probability changes to 3 over 51. And if you did not get an ace first time, then it would have been like 4 over 51. So you can see probability changes from trial to trial, simply because we are doing sampling without replacement. So this situation will arrive when you are doing sampling without replacement. That probability will keep on changing depending on what you have. So trials are not independent. You can see they are not independent. What is the probability second time will depend on what was your first outcome. If it was ace, then it becomes 3 over 51. If it was not an ace, then it would have been like 4 over 51. So first trial has an impact on the next trial. So that's why it is trials are not independent, and probability changes from trial to trial. So whenever we have that kind of situation, we use hypergeometric distribution. This is try it 4.2. I'm going to show you how to use hypergeometric distribution for these kind of situations. So there are a total of 200 balls in a bag that includes 25 red, 40 are selected randomly out of the bag, 8 of them are found to be red. Find relevant probability. So how to set this up, I'm going to show you. So there are some key numbers. Total is 200. So this is our total. You have 25 red and we have 175, like remaining. We can label them as other. They are taking a sample of 40. So let me capture that also somewhere here. So 40 selected, out of which they are saying 8 are red. So if 8 are red, then automatically remaining 32, 40 minus 8, remaining 32 are coming from here. Let us define a random variable x, which is number of red balls. And we are interested in what is the probability that this number is 8. Because they got 8. So what is the chance that number is 8? So how do we calculate this? So once you do 1 or 2 examples, you'll find it is very straightforward. We will need 3 combinations. In the denominator, 1 for total, and then in the numerator we have broken down into 2 parts, so we need 2. Denominator is 200, out of which sample of 40 selected. So how many ways you can select 40 out of 200? And then suppose first combination is for red. So we know that we have 25 here, out of which in how many ways you can get 8. And then other one is 175. In how many ways you can get 32. And once you calculate that, it will give you a probability of getting exactly 8 red balls out of 40. This is what I will write in R. Choose 25, 8 times choose 175, 32 divided by choose 200, 40. So this is what you will enter, and this will give you 0.058. Now there's no point in actually calculating them individually, because those numbers will be big and you will be spending a lot of time just entering them and getting them multiplied or divided. So simply enter the entire thing at once, and it says roughly 5.8% chance of getting a red ball out of 40. So TSA officers claim that they randomly select boarding passengers for additional search of carry-on luggage. So this is their claim, that they select people randomly. During past 1 hour, out of 100 passengers passing through the security point, 5 were silver-haired grandmothers, of which 3 were chosen for additional screening among the 20 total. So out of 23 of them were these grandmothers for enhanced vetting. Now calculate the relevant probability and comment. So the idea here is that are they really doing this randomly, or they are selecting some people, targeting some people very specifically, and their samples are biased. So how many passengers we have? So that is our total. And then 2 groups, 5 grandmothers, silver-haired grandmothers, and 95 are others. 20 was selected for extra screening. Out of that, 3 came from here, and obviously remaining came from this. So what we are interested in is the random variable x, which is number of silver-haired grandmothers selected. What is the probability that x is 3? So in a sample of 20, we want to figure out if it was really a random sample, what is that probability, and then see whether that probability is very low, very high, medium. So at least that will indicate to us whether the claim looks okay or not. Because if you get a very low probability of 3 getting selected, then a question mark comes up, like it may be that they are being selected in certain specific way. Again, we are going to break this down into 3 parts. So what should I write here? What is this number? Yeah.
100.
So that is 100. That comes from total. What is this number? Yeah.
20.
So that is 20. So the total sample size is 20. Now, if this one is for the grandmothers, what is the top number? How much? 5. And this one? So yeah, so we want to figure out in how many ways you can get 3 out of 5. So 5 and 3. And this becomes whatever is left over. So this is 95 and 17. So 95 and 17. So once you set it up like this, you will get probabilities very easily. So again, you plug in the values using that choose function that I showed you, and your answer is going to be 0.048. The probability is quite low, 4.8, like less than 5%. Less than 5% chance of selecting 3 grandmothers for extra screening. Those officers are claiming that they do this search randomly. Only 4% chance that they are selected randomly. It may happen that there's still a chance of 5% that it is random, but then you have to follow up next day and see whether there is a pattern, and then that will disclose whether it is just one random thing or really there is a pattern where those people are getting selected who have actually very, very low probability of getting selected. Now let me move to binomial. I will introduce this and then stop. So binomial is used where, as the name indicates, like bi means 2. So when you have 2 possible outcomes, like tossing a coin, you get head or tail. A customer going on Amazon website will click on buy button or will not click on the buy button. So 2 options.